Good morning, everybody. I'm really very pleased to be here with you and to share with you some of our activities and expertise and knowledge in the area of energy geostructures. I would like, first of all, to thank the organizers for their kind invitation. I really appreciate it and appreciate to be here with you. As it was mentioned, I'm head of Civil Engineering Department at the Swiss Federal Institute of Technology in Lausanne, and I'm also owner of a engineering consulting company that is specialized in the topic that I am talking about. So some of the projects that I will show you are projects coming from the company, not from my university side. So we are talking about the ground. And I was asked actually in this, for this presentation to limit myself to infrastructure. So I will talk about using energy geostructures in underground infrastructures, but we can use energy geostructures in other conditions that I will not discuss that much today. So actually, the key point in what I will mention today is the fact that almost all constructions that we do, we have to have them in the ground based. So we need to have foundations, we need to have tunnels for transportation, we need to have parkings, and other things. The key point in the energy geostructure technology is the fact that if you look to the temperature distribution in the ground, and this is a very fundamental point to understand what I will say later on, except the first part, let's say 2 to 5 meters, where the temperature could change during the seasons because it's affected by the external temperature. For instance, here you see various temperatures in the area of Lausanne in Switzerland, where in the winter the ground at the surface is almost at 0 degrees. In the summer we are almost at 30 degrees. And this is the spring and the autumn. But if you look, starting from 5 meter depth, the temperature is almost constant. It's not changing anymore. And this is true until a depth of almost 100 meters. After the 100 meter, temperature starts growing again, and this is what you know as the geothermal gradient, where we grow more or less by 3 degrees Celsius for each 100 meter. So what we are interested in is to use the fact that during 100 meter depth, temperature is constant all time. And this is a great, great advantage, because it means that if I take some of the heat that we have in the atmosphere and I put it in the ground, I can keep it there, that heat. And actually the ground has bad thermal characteristics, and this is we are happy with it. The ground is a medium where we can store energy. So if I take some heat in the summer that I put in the ground, I can use that heat in the winter to heat my buildings or to respond to other needs. I can do the same in winter, taking some cold. What I mean cold, it means a temperature that is lower than the ground temperature, that is constant all time. For instance, in all areas in this part of Europe, the temperature is constant between 11 to 13 degrees Celsius, depending on places, all over the year. So if you put in the ground temperature higher than 13 degrees Celsius, you can store them and can use them later on for heating. If you put temperature lower than 13 degrees Celsius, you can store them and you can use them for cooling. So this is the basic concept. It's very easy to understand and it's very easy to handle, and it works. So when we talk about geothermal energy, I would like just to make it clear, because sometimes there are confusions about what we are talking about, because we put a lot of things in the same basket. So actually, we can produce electricity from geothermal energy. But this is rare, because to produce electricity, you need to have in the ground temperatures that are higher than 130, 140 degrees Celsius. So to get those temperatures, you have just two possibilities: to go very deep, sometimes even 4 or 5 kilometers deep, or to be in places, volcano areas like Iceland, where you have such temperature almost at the surface. So producing electricity from the ground is another topic of geothermal energy. It's not related to geostructures that we are talking about. So what we are talking about in geostructures are rather shallow geothermal systems. So you have to keep this in mind when we have to compile the things. And then when we come to shallow geothermal systems, there are two families of those shallow geothermal systems. There are those that are well known, the borehole heat exchangers. Borehole heat exchangers are simply the fact that you dig a hole, you go to a given depth, usually 100 meters, 200 meters. There you will find a hot water, and then you will use that hot water to increase the heating of your construction. So for this, it's a technology that is different than the one that I will talk to you about that are energy geostructures. We are shallower, and here we are using the foundations or the infrastructure for this energy exchange. So not just to compare the two technologies, to have it clear in the mind of everybody. So from one side, I'm putting those borehole heat exchangers. From the other side, I'm putting energy geostructures. So just to let you know what are the difference. When you use borehole heat exchangers, you need to dig those holes, and it means that you need to use a specific space for them. And this space, you cannot use it later on for your construction. If you use energy geostructures, you don't need any additional land, because you are simply using foundations that in any case you are constructing to sustain your building. Or if you construct a tunnel, in any case you need your tunnel. You are not doing it for energy. So this is simply using something that is needed for civil engineering, and you use it for energy. This is just for energy. Such technology, borehole heat exchangers, allow you to heat, because you are taking temperature that's from the ground and you use it for heating. Energy geostructures has advantage that allows you to heat and to cool. So you can do both. So if you need cooling area, you can do it with this. Why is it possible? Because here, as I explained to you, the point is that we store the energy. For instance, if we have cold in winter, we can store it, and in summer, we can use it for cooling. This, you cannot do it because you are just extracting here. So here we can heat and we can cool. This is the second advantage. So this, as I was saying, this is related already to constructions that are needed for civil engineering, while this is completely separate from it. So however, the two systems use the same concept. The concept is that, of course, you can inject your 30-degree temperature that you have in summer, you put it in the ground, then with respect to the 30 degrees Celsius, maybe you have a delta T of 15 degrees Celsius that you can use the next time. However, you can enhance all this system by using a heat pump. So both systems use a heat pump. So actually, the system is based on what we call ground source heat pump. So the ground source heat pump is simply, we have to have exchangers at 3 levels. So for instance, we have the infrastructure, we are underground, so we can inject, for instance, in winter, we inject heat lower than the in-situ temperature, because we have around 5 to 7 degrees, for instance. We inject it lower than temperature, and by circulating our fluid in the pipes that we put in the infrastructure, we will come with some degrees higher because we store it some temperature in summer, or even if we don't store it, like the example that I'm showing here, I am simply using the ground temperature that, as I said, is all-time constant, equal 11, 12 degrees Celsius. So I come back with a temperature that is higher than this one, and here I put my heat pump. I put this first circuit in contact with the second circuit, so the temperature that I'm inducing here in the system is higher than this one by 2-3 degrees Celsius, not more than that. So this 2-3 degrees Celsius, now you come back to your thermodynamic concepts, and you know if you compress a fluid in an incompressible fluid, if you compress it, you will not deform the fluid, but you will generate heat, because this is the perfect law of thermodynamics. So we generate heat with the compressor. By putting under pressure our fluid, we generate heat, and this heat could be almost 4 to 10 times higher than the variation of temperature that we had here. So for instance, in the example that I'm showing here, we can come out with almost 40 degrees Celsius, even 45 degrees Celsius, with this simple example where I did not store heat, so I'm just using the heat of the ground. So and then with this, I could heat my construction, or can use this heat for anything else, and then I come back in the system. So this is what we call the ground source heat pump system. This is how it works. It's basically the same concept as a refrigerator that you have at home. There is nothing strange in it. It's the same technology. We use it for heating. We use it for cooling. The only point that you have to consider is the performance of the system. Is the system performing well? Why I'm asking this? Because to have this heat pump functioning, you need electricity. So I don't know from this electricity is coming from, but we need electricity. So now to say that the system is functioning favorably is when the ratio between the needed electricity, the needed energy for this electricity with respect to the energy that we are getting here, this ratio we call it COP, coefficient of performance. If this ratio is higher than 3 to 4, we have some projects where we have it at 5, 6, but if it's higher than 3, the system is very favorable. So so each time we have to check this coefficient of performance. So in my company, we specialize in those developing this system where the idea simply is to put heat exchangers in different kinds of infrastructures, in parkings, in tunnels, in railway tunnels, in foundations, and we can extract energy and we can store energy. What are the numbers that we have in various projects that we are dealing with? If you go for piles, for instance, linear things, depending on the areas, we have something like 4 to 150 watt per meter of pile. So this gives you a number. You can already multiply. You take any project, you see how deep are each pile, number of piles, and you come to a value of energy. In parkings, we use also the slabs. I will show you later on in some examples. We talk, as soon as we have area, or not linear, we talk in square meter. So 20 to 40 square meter, watt per square meter in such concepts. In tunnels, we are a little bit higher, 20 to 60 watt per square meter. So what do we do with this kind of heat? Actually, we have 4 main applications in the projects. We use it for heating and cooling, as I was mentioning before. But we use it also for hot water production. So you can produce it. We can use it for de-icing, because some amount of energy is enough to de-ice. And very important, we use it also for underground storage of energy. So how we use it also for underground storage? I mentioned before, by circulating this fluid, we get the energy that we have in the building. I just come back to the previous one. So just by circulating, we take the energy, the temperature that is, for instance, here in winter, and we put in the ground. But we can add to this, to combine it with other source of energy. If you think about solar panels are very efficient when the weather is nice, like this summer, for instance, during the day. In the evening, solar panels do not function. So they need a battery. They need to put their energy somewhere to use it later on. When we have a cloudy time in winter, solar panels are not efficient. So we can combine, and that's what we do, solar panels with the geostructures, with energy geostructures, to use the ground now as a thermal energy medium. So it's a battery. So they are the 4 main applications that we are dealing with this technology. So why is it important to deal with those kind of applications? Why is it relevant? Here I'm showing you statistics. They are the European use of energy. How we use in Europe energy. 1/4 of the energy in Europe is used for the building sector. 1/3 for transportation, and 1/4 for industry. And if we look to this building sector, which kind of energy are we using? 80% of the energy in the building sector is space heating or cooling and hot water. 80%. So when I was mentioning that we are dealing with those two kind of applications, it means with those two applications, we are covering 80% of the need of any building in the European atmosphere. So this is why it's relevant. But more than that, it was mentioned in the introduction later on, we are in this global warming situation. I think all of you are aware about the latest news of last week showing how the situation is bad. And actually with energy geostructures, and we got several international recognitions for that, we are simply saving a huge amount of CO2 by using such technology. This is first point. We have to keep in mind the financial component. We should not try to develop technologies that are not financially sustainable. And actually with energy geostructures, it is almost a free energy. The cost of it, it's almost nothing with respect to the cost of any infrastructure that we construct. I'm giving you here a range of values. Let's say maximum could be 1% of the cost of any new infrastructure. We showed in our project, and this is why we do optimization for several projects, that the return on investment, if it's well optimized, it could be already after 4 to 5 years. If it's not well optimized, it could be after 12 years maximum. So, and after this, for 50 years, you have free energy. The only thing that you will need is the maintenance of your heat pump. Otherwise, the energy is completely for free. So it's not only renewable energy, but in addition to that, it's an energy that is very competitive in terms of cost with respect to the other energies. Is a local energy. You don't need any transportation. So we are not counting here the transportation that we pay for other energies. And in addition to that, it gives also independency. You don't need to depend on what's happening in other places. If you import gas from Russia, and if tomorrow there are political issues, you don't need that. It's local. And this is why what I'm saying all the time to everybody, today, you should put those infrastructures, because as you saw, the numbers that I'm showing you here are numbers including design, calculation, and so on. But those infrastructures, just putting those plastic tubes, you should put them in any new construction, even if you are not using it today as an energy geostructure. Just put them. It costs nothing to put those tubes before putting the concrete. You will use them in 10 years. My prediction is that in 10 years, 15 years from now, any new building will have solar panel and a heat pump. It will be the standard for everybody everywhere. Everybody will be able to produce that energy locally. So we should start now by putting those plastic tubes, even if we are not planning to use them today. We will use them later on, because otherwise a little bit late to use them. So I was mentioning low carbon emissions. The investment is very low. It's a local. So of course, when I say it's a low investment cost, at the beginning, if you look to any project, just from civil engineering perspective, imagine that Madrid city is about to construct a new station for the metro, and they say, okay, this is the cost for the civil engineering. And you come at the beginning, you tell them, no, but you have to add something like 10% to the cost to invest also for analysis and design and putting tubes for energy geostructure. And they say, why? No, this is energy sector, it's not civil engineering sector. Why should we pay for it? It's the energy producer who will sell the energy that have to pay for it. But that one is coming later on. It will be a little bit late. So this creates issues in the projects related to energy geostructures in the sense that it's not conventional way. We have to change our way of establishing projects to allow new technologies to be considered. Otherwise, if we do them as we do it conventionally, we finish civil engineering, then we move to energy, then and so on. It's too late, because when you start to think about energy, you realize that you did not make the analysis needed for your infrastructure and you did not equip them. The equipment should be done from the beginning. Last point, cost saving compared to other energy systems. So we did broad analysis, comparing it with conventional and unconventional kinds of energy, renewable and non-renewable energies, and it's really something very competitive. And it's even cheaper compared to many other things. We estimate that, so it's Swiss francs is almost like euro, 30 euros per square meter per year of saving in the cost of your energy. So this concept by itself is very simple, as we were saying. You have simply to put connectors. The easiest way is to put them in plastic. They are plastic tubes. We circulate in them a fluid. The easiest way is to put the water. So it's a very easy system to put. You have to put it just close to your infrastructure, in contact with the ground, and then you put your concrete. So I call this elementary concept. I think it's very elementary. There is no complete. However, we have to take care about the design. It's not straightforward. The design is complex, and I will try to show you that also. So it's not because it's easy to put in place that it's easy to design and to analyze and to make it functioning correctly. So we have to take care by not too much simplifying also the things. It remains a technology that needs some expertise. So this is what we do in our company. We support architectures companies from the beginning in the conception and the way that we optimize where we have to put energy geostructure projects. We analyze the energy performance. It's very important to have a very reliable analysis of this. It's very important from the beginning also to do cost and return on investment analysis. This is also a key point, because we would like to have it renewable energy, but we would like to have it very efficient from financial perspective. Not only we are doing renewable because it's renewable. We are doing renewable because it's better than other technologies. And this is, we have to show it also from financial perspective. Something very important, and I will discuss it later on also, is that with respect to conventional civil engineering, for those who are with civil engineering background, usually when we construct things in civil engineering, we do not consider the temperature variation impact in the design. And all codes, including Euro codes, do not consider in their terms the temperature variation effect on the structural and geotechnical design. Here we are inducing ourselves this temperature variation. And this temperature variation could act like a new parameter in the design. And so this, you should consider it, even if there are no rules, no design codes at European level explicitly dealing with those things, but for any project we have to consider it. Implementation in complex consideration, conditions on site is something that is challenging and deserves also to be considered seriously. And very important aspect that usually we don't do actually in civil engineering infrastructures is the monitoring. Long-term monitoring of this infrastructure from energy perspective is very important for the optimization. Because all the design that we do at the beginning, we make a lot of hypotheses on the way that people will use energy in their building. We consider that someone will need an average temperature of 22 degrees in the day, 18 degrees in the night. This is in summer. We have a lot of hypotheses. And then when people sit at home, start opening the windows because it's too hot, and instead closing the generator. So then the users change the things. So by optimizing the way that people are really using the energy, by putting transducers during the construction of the project, then we get a lot of data that allows to optimize the system and make it more performant later on. So this is also something that we have to consider in analysis. Now, some technical aspects on the way how it functions. So this is, imagine any element in the ground, any concrete element. So here you see the concrete, you see the reinforcing steel bar surrounded by a soil or a rock. And basically what we are doing with energy geostructures is that we are putting those tubes, entering with a given temperature, going out with a different temperature. I said different temperature, 2 to 3 degrees Celsius. So we have energy aspect that we have to design because we are having this energy dissipation that we are having happening by this energy exchange. This energy dissipation first is happening in the tubes, then is dissipating to the structure. So we have a structural aspect in the design to consider, and then because the concrete is affected by changed temperature, and then it's going to the ground. So we have a geotechnical aspect to consider because often, friction, for instance, is a key parameter for the strength of foundation. So those three aspects are needed for a design of any energy geostructure. So you have to combine energy aspect, structural aspect, and geotechnical aspect. So let me discuss some design considerations. So if let's imagine here we have a station. This is a train station, for instance. This is here the area where trains were circulating, where people were circulating. This is the ground. This is our walls. What do we have in the system to analyze from energy perspective? We have a fluid that is circulating in pipes. So this is the fluid mechanics. Then we will have the temperature exchange that is happening between the pipe and the concrete. So this is dissipation of energy in a porous material. And then we have dissipation of energy from the concrete to the soil. Is dissipation of energy in a porous material with water and convection. So we have 4 typical materials: the heat in the pipes themselves, reinforced concrete, and the geomaterial, soil or rock. We deal with heat transfer, but we did also with mass transfer because we will control the flux here, what amount of water that we need to circulate in the tubes to have the needed amount of temperature. So we did with mass and heat transfer, and mainly here we are dealing with energy conservation and mass conservation. Then, when we are in infrastructures, there is a very important component that came, and it's very interesting for us, is the air. The air that we have inside the station will play a major role. I will show it in detail later on. So, coming back, we have convection in the tubes, conduction in the concrete, conduction in the ground, convection in the ground if we have groundwater flow, and convection in the infrastructure, in the area here. Those things should be mastered and should be controlled in such a way that allows you to design properly your infrastructure. So to do that, we simply use equations that are familiar for some of you. I'm sure this is the heat dissipation by conduction. This is the heat capacity. This is thermal conduction. If you have to have dissipation in the concrete and in the soil or rock, in the ground. However, in the tube, we have to have this exchange because we have a mass circulating, mass of water circulating, and there's a perpendicular component of the energy to the pipe that is important. So we have convection here of the fluid, and we have the generation of this fluid dissipation with temperature. So we have to master those two phenomena. One is purely fluid mechanics one in the tubes in non-isothermal conditions, and the other one is energy dissipation with convection and conduction. So they are the master questions and the elements that we have from energy perspective, and we can do that, obviously, often we have to do it in 3D conditions, and this is what we call thermohydraulic conditions. So we are combining the energy, so the thermal aspect, with hydraulic. And then we have the mechanics. So in the design that was done of our infrastructure, so everything was considered without considering the temperature change. So we have 2 effects that we have to consider. The first one is a frictional, in the sense that I will show you in detail, that the friction or the mobilization of strength will be affected by change of temperature. And this we have to control it and to know it. And then we have bedding moment that will be generated in the sense that temperatures will be different in different points, so the deformation will be different, so the moment will be different. So this is what we will see in the next slide. So we will have strain variation and stress variations that we have to compute, and of course we are dealing with equilibrium. So basically we have now to design our infrastructure to such conditions that were not meant. In conventional design, we do it like this, to have it there. As soon as you have temperature change, any body that you put in contact with change in temperature, either it will deform, okay? So then you have to deal with the deformation. Oops. You have to deal with deformation, or you do not allow deformation, you constrain it, so you generate stress, thermal stress, that you have to add to your static design. So the two things, and actually with energy geostructures, we are not in any of those two extreme conditions. We have a part of deformation that will happen no matter. We would like it or we don't want it. It will happen, and we have to master it and to control it. And we have a part of deformation will not be able to happen due to the rigidity of the ground and the system. Then this will transform in additional stresses that we call thermal stresses that we have to add in our geotechnical and structural design. So to do that, so we have to combine our energy equations that I showed you before to the mechanical one, where we have to add the thermal deformation. So here I'm just putting the thermoelastic deformation, but the plasticity, the thermoplasticity could be in the constitutive equation here. And this is the stress that we are getting in such things. So we have to redesign and recheck our structure due to this change of temperature, but this is the work of experts, so there is nothing special in it. So I will now show you two examples. I will discuss first part some project that we had on energy walls, and then I will discuss some project that we had on energy tunnels. So two examples of infrastructures. So when we deal with energy walls, basically the energy exchange system, so again, this is just cross-section. This is a symmetric line of our infrastructure. The energy that we can get from a system like this is the variation of temperature between the inlet and outlet temperature multiplied by a coefficient. This coefficient that we call it convective heat transfer coefficient is the key point in the whole design from energy perspective. Because as you can see, here you can control. There are two ways to design an energy system. Either you say, I would like this delta T, this variation of temperature, I would like to have it constant all time. So you put delta T, for instance, 3 degrees Celsius. So you control it on your heat pump, you put constant temperature. Heat pump will manage the needed flux such way you get all-time constant temperature. The other way around is to have constant flux. You say, I would like to inject all time the same hydraulic flux in the tubes, and no matter what I get in temperature. In the case of this part, we control it. This part is coming from the potential of your infrastructure, the potential of your concrete, the potential of your ground to give you energy. And you will see also the air in the tunnel play a huge role in this system. So this will help you also in managing the thing. So basically, keep in mind that we have a simple linear equation, but this coefficient here is not constant. This is a very important point to have in all design. From this perspective, this coefficient is not constant, depends on plenty of parameters that I will show you later. So when we have to design such energy walls, so here I showed you cross-section, where the pipes, we put them close to the ground. But actually, this is not all time the case. So we have to start by looking to different configurations. There are different possibilities depending on the energy capabilities of the soil or the rock, depending on the groundwater flow that you have there. Depending on that, you can optimize your system to get the energy that you would like to get. So you can get it, for instance, here, it's double U system. One is close to the ground, one is close to the tunnel. This is one option to the station. Other option is to put only one close to the ground. Other one is to put only one close to the station. Another system is that to make it impermeable from energy perspective in one of the two areas. You don't want energy exchange in one of two sites. This is we did it, for instance, in London metro station. To one exchange, you don't want it. This is something also is possible. So there is an optimization of those energy walls that should be done to get the best of energy that you can extract, but also looking to the cost of it. So of course, there are other, as soon as you decide where to put your tubes, for instance, if you decide to put them close to the station, which often we do, then we look to shapes. Different shapes, they will give different amount of energy. There is a small amount of cost in terms of length, but there is also operational way on how to put them on site in a way that you do not delay also the construction. The idea here is that each time we put a panel, so those panels here are more or less 3-meter length panels. Each time we put one, we would like to do it in 15 minutes. Otherwise, we delay too much the construction on site. So we have to be efficient also in the way to get. Then those panels, we try to have them to those tubes. Because if you go to see a seller of those tubes, or companies that used to put those tubes, they would like to put kilometers in one point, in one step. Never do that, because if you have a leakage here, you lose 1 kilometer of tubes. So usually we try to limit ourselves to 200 to 300 meters, but no more than 400 meters length in those tubes. So such way we optimize also, we have to consider this in the design and also in the feasibility. So, and based on that, I'm showing here, for example, the amount of variations of uncertainties that we can get. This is in watt per square meter of energy, depending on which solution you are considering. You see, you can multiply it by 4 to 5 times the same place, the same infrastructure. You can get almost 5 times more energy if you do it correctly. Then, from structural perspective, as I was mentioning, now we are having the fact that temperature is different from this side from this side of the wall. This side of the wall will have a given temperature that is different from the other one. So if you multiply each of those temperatures by the same delta, the same thermal dilation coefficient, you will get different deformations. So the deformations that we are getting will be different because we are having different deformation. So we split this in 2 parts. One, it's uniform deformation, because here we have uniform temperature. So we have entire deformation of our system in uniform way. But this deformation is not going just one direction, because also there is a trick when you hit a body. If you hit this stuff, it will deform from both sides. It will not deform entirely this way. It will deform in both sides. And there is a neutral point in the middle that will not deform. So then if you put it in the ground, actually you see that you have some constraints, some friction. So there is that what we call the null point, is the point that is not deforming, that will change the place depending on those conditions. So this null point, you should get it from the beginning to optimize your design, because you will have a part of the structure is going up, another part is going down. And there is a one point somewhere, depending on the rigidities and connections, that will not move at all. So those things you have to get them. And then the part of the temperature change that is not uniform, they create your curvative. So this creates your moment that you have to add in your design. So let me give you some examples that we are dealing with in the company on energy walls. I started with energy walls. So this is a project that we started last year. So we are in Monaco, and there is this tower that has to have a given amount of energy. The requirement was 230 kilowatt per year for this. But what I will show you mainly is that we have under it, we have this part that is a parking, 7-level stores. And actually in this project, what we did, because I'm limiting myself to the walls, so we have those 7 levels here of that parking, and we have an international school also here. It will be the International School of Monaco. And actually the saturation conditions are not uniformly distributed. We have a dry area at the top, and we have an unsaturated one here, and then we have a saturated one. And actually, when the material is partially saturated, the thermal conductivity and the heat capacity decreases. So we have, because they are dependent on the degree of saturation, so we have to consider this in the analysis. So actually, and here you see there are the piles and the barrette. And what we did, to get the goal, this was the goal of the owner of the building. He asked us to provide this amount of energy. Not less, but not necessarily more. Because to get this, he got a reduction on taxes. Because the building is considered later on as a green building in given perspective. So the building will pay less taxes. So we equipped energy walls. We equipped more than 3,000 square meters here of energy walls. We had 165 piles in the entire construction. We equipped all of them, but we did it with the same length for all of them. So we did it just on 10-meter length. It was enough, and we had those barrettes. They are big piles, actually. We equipped 5,800 square meters. And with those things, with those conditions here of saturation and water flow, here we are close to the sea. Actually, the sea is just here. At less than 500 meters, so we have the water flowing here under. We were able to provide this amount of energy. This is another example. So this is a project we are working on currently. This is in Seoul, in Korea. We are downtown, so we are in the city center. And here we are designing this infrastructure that will be entirely equipped with energy geostructure. But we are having various options. I will show you later on. So this is 1 kilometer length. Here we have a conference center. There is a mall here, and there is a station here, underground station. Actually, there are 2 levels. There is underground station and train station in the same place. You will see it in the next slide. So this is how it looks like. This is our 1 kilometer project. So it's here, it's entirely in glass to have lighting coming from, natural lighting from outside. The idea here is that we will have around 8,000 people in this part daily, in this part of the infrastructure, 22,000 in this part, and 10,000 in this one. And then we can add to them. So altogether, we have to provide almost constant temperature over all the year for 60,000 people. This is the challenge that we are dealing with, and we are happy to deal with because we showed that it's feasible. So, and I will show you this. So this is a cross-section of our project. You will see it later on because we have different entrances, and you have this part that I will show you that is completely in glass. And the idea was also to avoid to have snow on it, because if we have snow on this glass, then the lighting will decrease. So the idea is to avoid to have it to have snow. So this is a cross section. This is this part with the glass, as I was mentioning. So here we have bus and cars running. So we have this air exchange that we are looking for, and I will show it more when we show the tunnels later. This coefficient. We have the people running here. Here we have the trains, and we have the metro here. So what we did in this project, we create what we call it a thermal labyrinth. This is our project, how we solved it. So this is our glass beam, as I mentioned. So here we put also energy exchangers. So all those points that you see are energy exchangers. Here for de-icing. I mentioned before that we can do de-icing, so we did it here. Otherwise, here we have piles. So the entire piles are equipped for energy exchange. We left some space here for air circulation. Here we have slabs. A part of the slabs, we are using them for cooling. Part of them are using them for heating. And this system is not a conventional way of doing the things where you are saying, I'm heating my house, for instance, or my building and cooling it. Here, the idea is to keep constant temperature all over the year, no matter which are the temperatures outside. So in Seoul, they could be very cold and they could be very hot. So we create all this labyrinth with all this air circulating, allowing to have constant temperature, and all energy, all of it, is coming from geostructures, from infrastructure and geostructures. So there is no other kind of energy in the project, and this allows to have the entire temperature constant over the year. So I will not go details because we did several scenarios for this, and depending on scenarios, we did different, because there is financial optimization, the system that we had to do to convince the client that this is the best solution of it. So on the end, this is the final construction, how it is. So we did not equip the entire system because it was enough. Actually, we had, I will show you next slide, we had enough energy for getting constant temperature from the entire 1 kilometer long just by having this part that is the green one that you see here was enough for us. So this is the final design that we did for the project. So here we use all this part for cooling. Here our energy walls, energy slabs. We used also this exchange of energy coming from the air, from those. This is railway tunnel, this is train tunnel, and this is the metro line. And here you see the numbers that we developed and the things that we developed. And this allowed to give an award like Platinum, LBB recognition for the solution. So this is the final solution that we are getting, and these are the numbers maybe that are of interest for you. So we are getting, for heating, more than 4 megawatt for the project, cooling 3.5 megawatt, by equipping something like 45,000 square meter of walls and piles with tubes. This is basically the project that you see. So we have the slabs that I showed you that at the bottom, at the top. We have the walls, because we are interested in the walls in this part, and we have the piles. Another example of energy walls. So I was involved in the project which we call Grand Paris. So in Paris, they are constructing 3 new metro lines. Initially, they were meant for the Olympic Games 2024. Now, for budget restriction, they decided last summer, so 1 year ago, to extend the construction until 2030. So not of them will be ready for 2024, but they maintain them. So the 3 new metro lines, there is extension of line number 14 that currently is stopping at the library François Mitterrand, so it will be going to the airport of Orly, and they are number 16 and 17 and 15. So in those metro lines, we analyzed initially 16 stations, and I will come back later on for metros, 16 stations to be equipped just on the line 16. So I will show you some examples with just some numbers to highlight the things. This is a large station, Saint-Denis-Pleyel. Saint-Denis-Pleyel is somewhere, it's here. It's a large station because it's connection of 3 metro stations. And there, you see, the power that could be get it's almost 700 kilowatt, and there is almost 200 that is not used. And actually, the point here is that those stations do not need energy. They are stable from heating and cooling perspective. So stations do not need energy. So the point is that now is to sell this energy to the surrounding area. And we know until 500, 600 meters surrounding the place is possible to provide energy. So the idea is that, because those new stations are constructions in areas where there is nobody living today. So they will expand Paris to the north with those stations. So the idea is now to provide this amount, 13,000 square meter of construction, so surrounding it and until going until 23,000 square meters of residential blocks that will be constructed later on to connect them and provide them with the fact that we could equip 12,000 square meter of the energy walls. So we go a little bit faster. And yeah, of course, we did numerical analysis for the optimization, showing you as we did before with those finite element codes that we developed with all the equations to optimize the system. Another station, this is smaller station, La Courneuve, it's left side on the map. It's just 1,700 square meters that could be equipped. And again, you can see it here, the kind of energy walls that we can get, and this is cross-section horizontally. Another station, Le Blanc-Ménil, 5,000 almost of energy walls that you can see here. You see it's three-level station, and here we put also slabs as energy exchanger. Last example of walls, this is a project that we are having in Switzerland. So this is Geneva Airport here. This is Geneva City. This is a new metro line. It's at the end of the construction. Some stations are already open, connecting Geneva to France, to Evian. So, and there I will show you an example of an energy station. So I will show you, this is Genève-Bachet station. You see it here. It's equipped with this energy geostructures. And now we are in the stage, the construction is finished, calculation done. Now we are in the stage of optimization. So the owner of the station, which is the electricity company of Geneva, they had some calculations and so on. Now they would like to ensure what is the amount of energy that they will sell from the station. So, and they will start selling the energy in 2019, so end of next year. So, of course, we did all calculation and design and so on. And then during the design, we consider that slabs and walls are giving between 10 and 20 watt per square meter. So currently, we are going to the real conditions in the sense that we are off. Yeah, and also one of the big challenges is that we are close to the as you can see it here, this is Geneva Lake. Of course, yes, we have the groundwater playing a role. So just to ensure that the initial design that we did makes sense, okay? So because the groundwater may dissipate the energy in the thing. So just an information on the station. So the total energy that we can get from it is more or less around 200 kilowatt. Here are the numbers that were equipped with energy geostructures. You see them better here. So energy walls, we have 4,000 linear meter if we look at it like this, and 3,800 square meter activated energy slabs. So this is the cross section of the station, and you can see it here also. So as I mentioned, so currently we are another stage, a stage of optimization on site. So construction is finished, transducers are there, and so on. So we are doing what we call a thermal response test. Thermal response test is very conventional for piles, but when we come to structures like this, you cannot use the conventional thermal response test because the linear linear source equation that we used to use do not apply in those conditions. And here we have the entire condition. So the idea is that to equip during 1.5 years the station with those transducers that we put there, that you see here. We put temperature transducer, air velocity, deformation. So this is the station now. Those pictures were taken last week. So, and here is this glass wall, and we have here 70 centimeters where we are putting all our equipment on the wall here. And yeah, we have already the pipes there and so on. And the idea is that during 1.5 years, we will optimize the system and we will give a response to the electricity company on really how much they can relay in winter and in summer, because their job is to sell this energy. So for the 5 last minutes, I will show something about tunnels. Okay. So tunnels are different than energy walls. Of course, we have this air that plays a role. Also, we have the ground, but the exchangers are put in, and there are two kinds of tunnels. There are two kinds of ways to put the tunnels. So in any case, the equation that we use remains the same. This is nothing changed. The energy could come either from the ground, as we saw it before, but also from the tunnel by itself. So we have to combine those two sources of energy, and actually this coefficient H is not constant in the sense that depending on the velocity of the air and the hydraulic velocity, so we have a thermal velocity, thermal development in the tunnel, and we have hydraulic development of the air in the tunnel. And those two are not designed the same way. Because the idea is that we get more energy when we are in the fully developed region. So when the system is completely in kind of steady state conditions, there we get the maximum energy. As soon as we have to change the trajectory of the tunnel, then we are in what we call entrance region, and the energy from one side and the hydraulic of the air in the tunnel are more affected by the frictional conditions. So this is why even the concrete that you put, rigidity of the concrete that you put in the tunnel play a role on this coefficient H that I was showing before. This, we show it in different projects, that the way that you put your concrete, your shot concrete, for instance, in the tunnel, plays a role on the amount of energy that you can get. So we have to design the things depending on the trajectory of the tunnel, whether it's in this entrance region, and as I said, the thermal one is different than the hydraulic one. Hydraulic is the air convection. So to do that, we use, for instance, here we use codes that are in the market, actually. It's a fluid mechanic problem from one side, it's air diffusion, energy diffusion, that we combine with other codes dealing with structure and with hydraulics. And we show that this coefficient H that we have seen before is not a constant one. For instance, it depends on the air velocity. So depending whether your trains are running fast, if you are doing, I'd say, a fast train station or metro station, depending on number of stops of the train, how it's decreasing the velocity. We consider also that this coefficient is different in night and day. For instance, in metro station, during the day, you may have a lot of fluxes. So there are a lot of trains. During the evening, you will have less. In the night, you have almost nothing. So this coefficient, we change it almost every 5 to 10 minutes when we have to optimize our design of the infrastructure. So then we can run calculations and so on, so this is not that important. And we show that the way that we put our tubes has importance on the amount of energy that we can extract. So we can see here, we can extract almost 4 times more depending on the way that we put our tubes. And we apply this technology to a Grand Paris Metro project to a tunnel that is here in the station that's called Shell. So there actually on the market you can find 2 kinds of tubes, so 2 kinds of diameters, 20 millimeters or 32. So we consider 2 of them, and we consider different positions of our tube with respect to the ground or the entrados. So we have different distances, and we considered different velocities of the fluid, the water, in the tubes. So this is Reynolds number. So we are all-time turbulent because turbulent is more efficient for energy exchange. But depending on this, we optimized the way to allow us to extract the maximum energy from the system. And from this, we related to financial aspect to say, in euros, because it was in France, what are the configurations that allow us to be profitable? This is on the top. But there are even configurations. So you can have projects where you put energy geostructures, but you are never profitable. You never recover your money if you don't do your design correctly. You see, one of the configurations here, you see 2 of them. Even we equip them, we have energy exchange and so on, but financially we cannot recover. So here you see that you can have those who can recover, those who cannot recover. So such analysis is absolutely needed. Last example, this is a new metro line in Lausanne, in my city. So we have this line red here that is constructed, and I would like to show you because we did some interesting analysis also for this part that I would like to show you. This is our metro line. Actually, the metro line is going at different depths with different hydrology. So in one case, for instance, we don't have water at all. We are at depth of 25 meters. Other cases, we have a water table at this level, others at this level. So in all conditions, this part was a little bit shallow. We have to analyze all things, and we are proposing to equip 60,000 square meter of this tunnel. So you see we equip the part here and the slabs also. And what I would like to show you is that in this analysis, we were able also to provide the cost of energy at which this energy could be sold depending on the distance from the metro line. So if, for instance, if you are close to the metro line, the cost of energy would be around 16 cents per kilowatt hour. If you are a little bit farther, it's a little bit more expensive, and so on. And this is also very important from an economical perspective to sell. It's not the same cost if you have to equip a construction that is just close to your metro line or if it's at 500 meters of it. And then also we calculate the amount of thermal power that we can get, the amount of CO2 saving, but this does not play a role, unfortunately, when we have civil engineering constructions, because at the beginning, when we vote for a project, we do not count the CO2. And to conclude, I would like to say that energy geostructures, from my perspective, is a mature and even powerful geothermal solution that we should use in any case. And we should equip any infrastructure with those pipes, even if we are not using it today as energy geostructures. The concept is very basic, but if you would like really to have it seriously done, you have to design it properly and optimize it from energy, structural, geotechnical, also financial perspective. If you are interested to know more, I'm giving an intensive course every year for people from industry and academia in Lausanne, so you are very welcome to join, and thank you very much for your attention.